to Math 143, Finite Mathematics. In the previous lecture, we introduced sets, elements, subsets, unions, intersections, complements, and Venn diagrams. Today, we are going to use those ideas to answer counting questions. Okay, what are the counting questions? So, for an example, let's see the counting questions. How many students take at least one of two courses? How many people prefer at least one of several products? How many elements are in a union? How do we avoid counting the same person more than once? So these questions lead us to the additional rule and the principle of inclusion-exclusion. By the end of today's lecture, you should be able to determine the number of elements in a finite set, apply the addition rule for two sets, recognize disjoint sets, apply the principle of inclusion-exclusion for three sets, find the number of elements in a complement, and solve word problems involving overlapping groups. Okay, then let's begin with the notations. So the number of elements in a set. If A is a finite set, then the number of entries, number of elements in set A can represent by NA, means the number of elements in set A. Okay, then see the example. For example, set A contains 1, 2, 3, 4 elements. There are 4 elements. There are 4 elements. So, the number of entries in set A equals 4. So, we are not adding the elements, we are simply counting how many elements are present in our set. Okay, then let's go for the next example quickly. Let set B contains 2, 4, 6, 8 and number 10. What is the number of elements? What is NB, the number of elements in set B? So, the number of entries or number of elements in set B, 5. Just count how many elements are present in set B. Okay, let's recall the union and intersection before introducing the counting formula. So recall union of two sets. So let's say let A and B are two sets. Then the union which represent A union B, so contains elements in A, in B or both, in both. Okay, then next the intersection. Of two sets. Again, A and B are two sets. Then the intersection A intersection B contains elements common to both sets. Okay, this overlap is very important when we count elements in a union. So let's go for the addition rule for two sets. Addition rule for two sets. Suppose we wanted to find the number of elements in A union B. Let A and B are two sets and we want to find the number of elements in A union B. That is the number of entries in A union B. Okay, in a natural, first idea is to add the elements in A and elements in set B. Elements in set A and elements in set B. But this creates a problem. Let's think about, we have the Venn diagram representation. We have the Venn diagram representation, set A and set B. A, B. Okay, a natural first idea is to add the number of entries in A plus number of entries in B. Right? But every element in intersection here, when we add the number of entries in set A and set B, the every element in the intersection here, every element in the intersection here belongs to both sets. So it gets counted twice. To correct the double counting, we subtract the intersection once. Then, this is wrong. The addition rule is, number of entries in A union B equals number of entries in A plus number of entries in B minus number of entries in A intersection B. So this would be the addition rule. The addition rule. Okay, why do we subtract the intersection? Why do we subtract the intersection? Why? Let's make the logic very clear. When we add number of entries in A and number of entries in B, elements that belongs only A are counted once. Also, elements that belong only B are counted once. But elements in both A and B are counted twice. So subtracting the number of entries in A intersection B removes the extra count. Okay, let's see the county example. Let the set A is 1, 2, 3, 4, 5. Set B 4, 5, 6, 7. Okay, first find the intersection. A intersection B. The set contains the common elements 4 and 5, just 2. Therefore, number of entries in A intersection B equals 2. Now, count each set. The number of entries in set A. How many elements in set A? 5. Number of entries in set B. 4. Apply the formula. The number of entries in A union B equals number of entries in A plus number of entries in B minus number of entries in A intersection B. 5 plus 4 minus 2, 7. Then check by listing the union. A union B, the set in A, B or both 1, 2, 3, 4, 5, 6, 7. How many elements? There are 7, right? There are 7 elements. So we justify the answer. The number of entries in A union B for the given example, 7. Okay, let's move forward. The next example, example 2. In a class, 18 students take mathematics. 12 students take stats. Also, 5 students take both. So, let's write the notation. Before that, let M students take in math, S students take in stat. Then the number of entries in set M, 18. Number of entries in set S, 12. Number of entries in set M intersection S, 5. Okay, then let's move towards. We wanted to find out how many students take at least one of the 2 subjects. Okay. How many students take at least one of the 2 subjects? The phrase at least means the union. The phrase at least means union. Math or stat or both. Therefore, the number of students take math or stat, the union, number of students in math plus number of students in stat minus the intersection. So let's substitute the values. 18 plus 12 minus 5, 25. So 25 students take at least one of the two subjects. So 25 students take at least one of the two subjects. Okay, then I would like to draw the Venn diagram for this case. So let's go for the Venn diagram. We have the universal set. 18 students take math. Let's say the mathematics and statistics. Okay, in total, the mathematics circle contains the number of students 18. In total, the stat circle contains 12 students. In total, the intersection part contains how many students? 5. Then the entire circle value, the sum of the entire circle numbers equal 18, the number of students. Then only this space equals 18 minus 5, 13. Okay, then only this space equals 12 minus 5, 7. So, how many take only mathematics? How many take only math? How many? There are 13 students, 18 minus 5. So, 13 students take only mathematics. How many take only statistics? There are 7 students take only statistics. Okay, then let's recall the disjoint sets. We already discussed the disjoint sets in our previous section. If the two sets are disjoint if they have no elements in common. Two sets are disjoint if they have no elements in common. So that means A intersection B is empty set. There is no intersection. Therefore, the number of entries in A intersection B equals 0. Then the addition rule simplifies to the number of entries in A union B equals number of entries in A plus number of entries in B, because the number of entries in A intersection B equals 0. So this is a very important one. The addition rule simplifies to this for disjoint set. The disjoint sets are sets they have no elements in common. Okay, let's go for the example quickly. Example, let set A 1, 3 and 5, set B 2, 6 and 4. Okay, then what about the A intersection B? These sets are disjoint. So the empty set. Therefore, the number of entries in A union B equals number of entries in A plus number of entries in B. So 3 plus 3, 6. Okay. If two sets are disjoint, should we subtract anything? No, because there is no overlap. So let's represent the two sets A and B. They are disjoint. That means no common outcomes. Okay, let's move forward. Again, recall the complements. Complements. So let A be the set, then A complement contains everything in the universal set that is not in A. Therefore, the number of entries in A complement equals number of entries in universal set minus number of entries in set A. Let's see the example. Suppose the number of entries in universal set equals 50 and number of entries in set A equals 32. Then the number of entries in A complement equals 50 minus 32, 18. So 18 elements are not in A. Right? Okay, up to this point, we only discuss about two sets. Then let's move towards the three sets. The same double counting problem becomes more complicated when we have three sets. If we simply add the sizes of three sets, elements in pairwise intersections are counted more than once. So let's see the figure here. You can see the set A, set B and set C. Let's say A, B, C. What about the pairwise intersections? So this one, and this one. What happened? If we simply add the sizes of the three sets, elements in those pairwise intersections are counted more than once. Then the triple intersection creates an additional correction. So this leads to the principle of inclusion, exclusion. So inclusion, exclusion for three sets. Okay, we don't want to go for the proof. Just think about for three sets A, B and C. Then the number of entries in A union B union C equals number of entries in A plus number of entries in B plus number of entries in C minus number of entries in A intersection B, number of entries in A intersection C, number of entries in B intersection C, plus number of entries in A intersection B intersection C. So, the pattern is add the three individual set sizes, subtract the three pairwise overlaps, add back the triple overlap. Why do we add the triple overlap back? Because it was initially counted 3 times and then subtract 3 times. At that point, it has been counted 0 times. So we add it once. Okay, let's see the example. Suppose the number of entries in A, 20, number of entries in B, 15, number of entries in C, 12, number of entries in A intersection B, 6, number of entries in A intersection C, 5, number of entries in A, number of entries in B intersection C, 4, and number of entries in A intersection B intersection C equals 2. Then find the number of entries in A union B union C. So you can directly solve this using inclusion exclusion for 3 sets equals NA plus NB plus NC minus NA intersection B minus NA intersection C minus NB intersection C minus NA intersection B intersection C. Okay, what about the values? 20 plus 15 plus 12 minus 6 minus 5 minus 4 plus 2. 34. The number of entries in A union B union C equals 34. Okay, let's go for the wording example. Among 100 students, 60 like coffee, 45 like tea, 30 like juice, 20 like coffee and tea, 15 like coffee and juice, 10 like tea and juice, 5 like all 3. Find the number who like at least 1 drink. Who like at least 1 drink. Okay, before I apply the inclusion exclusion rule, let's draw the Venn diagram. It is important to know how to draw the Venn diagram. So we have 3 sets. Then let's say the universal set here. The universal set contains 100 students. The number of universal set, total 100. And within the rectangle area, we have 3 subsets: tea, coffee, and juice. Okay, the question says among 100 students, 60 like coffee. So that means this entire circle, this space, this space, this space, this space, all 4 spaces the total of all 4 spaces equals 60. Right? Equal 60. Also, 45 like T. That means this space, this space, this space, this space, all 4 space, the number of persons in all 4 space equals, the total equals 45. Total, right? Also, it says 20 like juice, the total in all 4 spaces equals 30. I'm sorry, it's 30. Okay, then let's go for the unions. 20 like coffee and tea. 20 like coffee and tea. So coffee and tea, which represent by this entire region, that means the sum of this space and this small in space equals 20. Equals 20. Total, right? Equals 20. So 20 here. Also, 15 like coffee and juice. 15 like coffee and juice. That means this entire space, including this and this, 15. Okay. 10 like tea and juice. That is, this entire space, including this and this, equals 10. The entire space equals 10. Also, 5 like all 3. So, all 3 contains this space. So, the number of persons in that space equals 5. Then you can easily see that the entire space here, 20, 5 plus 15, 20. This entire space 15, 5 plus 10, 15. This entire space 10, 5 plus 5, 10. This entire circle equals 45. So 45, then 20 here. 20, 25, 30, 40, 45. This entire circle here 30, 10, 15, 20 and 10 here. This entire circle equals 60, 15, 20, 30, then 30 here. Then you can easily find out all the values. The persons who like tea only, persons who like tea and coffee only, persons who like juice only, persons who like coffee only, everything, right? Okay, let's apply the inclusion-exclusion formula. Okay, that is the number of persons like coffee, union tea, union juice, that is NC plus NT plus NJ minus NC intersection T minus NC intersection J minus NT intersection J minus NC plus NC intersection T intersection J. So 60 plus 45 plus 30 minus 20 minus 15 minus 10, right, minus 10 equals how much? 95. 95. In total, the union, that is the entire space here, equals 95. Out of 100 persons, out of 100, 95 persons including all three, that is outside only 5 students. Therefore, 95 students like at least one drink. Therefore, 95 students like at least one drink. Also, 5 students like none of the 3 drinks. So, please make sure to understand at least one and none. At least one means union. None means the complement of the union. So, if the universal set U the number of entries in A union B union C complement equals number of entries in the universal set minus number of entries in A union B union C for 3 sets. Okay. For additional practice, I will give you more practice questions. Exercise 1. In a survey, 40 people like basketball. 35 people like soccer. 15 like both. Then, first question, how many like at least one sport? Second, how many like only basketball? How many like only soccer? Pause the video and solve. The answers, I would encourage you to draw the Venn diagram first. We have 2 spaces, basketball and soccer, 2 sets, right? Okay. The entire basketball circle contains 40, entire soccer circle set contains 35. 15 like both, the intersection, then 25 here, 20 here, right? 25 plus 15, 40, 15 plus 20, 35. Then, first question, how many like at least one sport? So, that is the number of entries or number of elements in both basketball and soccer. So, NB plus NS minus NB intersection S. 40 plus 35 minus 15. How many? 60. 60. If you wanted to check it, you can add all three spaces, 25, 15, 20. 25 plus 15 plus 20, 60. Right. Then question number 2, how many like only basketball? It is easy to read only basketball within the Venn diagram. So you can read only basketball space here. So the number of entries in only basketball equals 25. Only soccer, it is easy to read it from here. Only soccer, 20. So that's why I encourage you to draw the Venn diagram before answer the questions. Okay, one more exercise. Suppose the number of universal set 80, number of elements in set A 45, then find the number of elements in A complement. The solution, pause the video first and try it by yourself. The number of entries in A complement equals number of entries in universal set minus number of entries in set A. 80 minus 45, 35. Okay. Then one more question. Exercise number 3. Statement 1. Statement 1. If A and B are disjoint, then number of entries in A intersection B, set A intersection B, 0. Is it true or false? It is true, because the two sets are disjoint means there are no common outcomes. Statement 2. The number of entries in A union B equals number of entries in A plus number of entries in B always. Is it correct? True or false? False. It is true only when the sets are disjoint. Okay, before end the today lesson, I wanted to discuss the common mistakes. So the most common mistakes are forgetting to subtract the intersection, subtracting the intersection twice, confusing union with intersection, forgetting to add back to triple intersection in 3 sets formula, using the total population as the union, forgetting that none means subtracting the union from the universal set, treating pairwise intersection as if they exclude the triple intersection unless the problem says only pairwise intersections, using include those in all 3 sets. Those are the common mistakes. Please keep this on your mind. Then let's summarize today's lesson. The notation NA represents the number of elements in a finite set, set A. For 2 sets, the addition rule is used to count the number of elements in at least one set. We subtract the intersection because those elements were counted twice. For disjoint sets, the intersection is empty, so the set size can simply be added. For 3 sets, we use the principle of inclusion-exclusion, add the individual sets, subtract the pairwise intersections, and add back the triple intersection. We also learned that the number of elements in a complement is found by subtracting the size of the set from the size of the universal set. These ideas are extremely important because they will be used again when we begin probability. Thank you for watching. I'll see you in the next lecture.